Well, here's the second part of section 3. We'll start with motion problems. And there's a couple formulas, or basically the same formula put into three different solutions. So you solve for d, which is a lot of times we see it that way is distance equals rate times time. Well, if I solve that equation for r, I'd get r equals distance divided by time. And if I solve for t, I could get distance over rate. And those are the kind of problems that we do that I'd say, oh, well, in this case, if I want to know the rate, if I was traveling at 60 miles an hour and I traveled for 3 hours, this would be the form that would tell me what the distance would be. So I'd say the distance equals 60 miles per hour times 3 hours. So it'd be 180 miles. And I'll show you a couple things that happen with labels and stuff with fractions. Fractions are really important when it comes to um, these labels and stuff like that, because in actuality a rate is a distance times time, and that's this formula right here, or distance over time. And if you look at, in this case, it's going 90 kilometers per hour. That means for every, basically that's a fraction. It's 90 kilometers over 1 hour, and so on. But these are important when it comes to motion, so you need to know these formulas. We're going to use this. So let's look at this first train travel one. Example 6. It says a Vermont Railways freight train loaded with logs leaves Boston heading to Washington, D.C. at a speed of 60 kilometers per hour. 2 hours later, an Amtrak Metro line leaves Boston bound for Washington, D.C. on parallel track at 90 kilometers per hour. At what point will the Metroliner catch up with the freight train? Okay, so they say first familiarize, or we want to look at this. What do we know from what they've just told us? They say let's make a guess and check to see if it's correct. Suppose the trains meet after traveling 180 kilometers. We can calculate the time for each train. So in other words, they take this time formula in a sense. They're going to say, well, if we went 180 kilometers at this rate, you would divide by that rate, and that would be using this formula right here. And you'd get 180 over 60, and the kilometers actually would cancel out, and you'd end up with just hours. Okay, and you end up with 3 hours. So in other words, the freight train in to go 180 kilometers, it would take 3 hours because its rate's right here. The Metroliner would go 180 kilometers in 2 hours. Okay, so we got some information, and if it wasn't for this other fact that the Metroliner, the Amtrak train, didn't leave the train station till later, right? 2 hours later. So in other words, what would really happen if, in this time frame thing here, is this train will have traveled for 5 hours by the time this train travels for 2 hours. Or excuse me, yes. Okay? Because this train doesn't start for another 2 hours. So how do we represent that algebraically? So we're going to have to try to get a system of equations out of this thing. We see the distance cannot be 180 kilometers since the difference in travel times for the trains is not 2 hours. Although our guess is wrong, we can use a similar chart to organize the information on this problem. Distance at which trains meet is the distance is unknown when they meet, right? But we do know that the trains will have traveled the same distance when they meet. That's a pretty important fact. So in other words, d, distance, will end up being the same for both of these equations. Now the time that the trains are running is also unknown, but we do know that the freight train has a 2-hour head start. Thus, we can let t equal the number of hours the freight train is running before they meet. Then T minus 2 would be the number of hours the Metroliner runs before catching up with the freight train. Now let me say that again. You have the freight train takes off, right? And then 2 hours later the Metroliner will take off. Well, to represent time in the same, to have a quality of time, right, is, well, we just put the T minus 2. So after this freight train runs for 2 hours, how long has the Metroliner ran? You kind of check it that way. You say, well, it would be T minus 2, or 2 minus 2 is 0 hours. In fact, it would. I mean, that train hasn't left the station after 2 hours. It's just leaving. So it hasn't run any time at all. If the freight train ran for 4 hours, the Metroliner would be going for 4 minus 2, or 2 hours. Okay? So we're getting expressions to represent the situation for these two trains. So we can put this into a chart, and the formula equals, this distance equals rate times time, guides us on where the rows and columns can be. And it's not necessarily true, but that you have to exactly do it this way, but that's a good formula. That's the most common formula. You could do actually one of the division ones too. But this is nice because it goes here as a freight train. If it went a certain distance, it would equal the rate times the time. So here it is with 60 times t. So d equals 60 times t. The Metroliner would be the distance equals the rate times this time that's in relationship with the freight train, because this train doesn't leave for 2 hours later. So we get these two equations right here. And now that we have two equations, we can solve those a couple of different ways, right? So they use substitution, which is a very good strategy because we have it solved for d. So I could take the d here, which is equal to 60t, and substitute it in for this d, right? And put 60t in here, and that's where they get this. So they took the 60t from d in the equation. It says 2, but I would say the 60t came from equation 1 and then put it into 2. Maybe that's what they mean. Well, now we have an equation with one variable, and we can solve that, and we get t equals 6. Now what does that mean? T is the time the freight train has been running, right? So it means the freight train ran for 6 hours, right? So how long did the Metroliner run? Well, it would be that time minus 2, because it sat in the station for 2 hours after the train left. So it ran for 4 hours. Remember that it is distance, not time, that the problem is asked for. In other words, this is a very important deal, is we do all this work, and I've seen really good work, a lot of stuff, and then don't answer the question that's asked in this word problem. But they're asking for distance here. So we check. So, well, we can take this time of 6, and if we want to find out, or t really is 6, right? Well, I can put it back into the original equation, and I get distance equals 60 times 6, or 360 kilometers. Well, we could check the freight train that way, and also it would be pretty important that the distance of the Metroliner would have to be the same. And if they weren't the same, then I have an error, because that's exactly what has to happen, is these trains will have to travel the same distance. So in 4 hours, or this t minus 2, you just put the rate times t minus 2, or 6 minus 2, and I get 360 kilometers. So the numbers check. So we have a solution. This is basically, it is telling us how far these trains have to travel before they go the same distance. Now, that was the train problem, is they're going in the same direction, they're in parallel tracks and that kind of stuff. Now this example is when we have things approaching each other. So they're talking about these Boeing 747-400 jet flies 4 hours west with a 60-mile-an-hour tailwind. Returning against the wind takes 5 hours. Find the speed of the jet with no wind. Okay, I guess I just looked at the picture and assumed it was two planes, but this is one where it's going with the wind, and here's where it's coming back against the wind. So this is a nice picture. I don't think I would draw the whole jet airliner and stuff like that, but I could show a plane, and I could say when it's going this way, it has a tailwind, or the wind is in the same direction as the plane, and it speeds the plane up. And when it returns against that wind, it'll slow it down. And they talk about ground speed in terms of that. Okay, so we got a pretty good idea what they're talking about in this problem. Let's make a guess of 400 miles per hour for the jet speed if there's no wind. So basically we're taking some kind of example that would make sense. So they said, well, the speed with no wind is 400 miles an hour. The speed with the wind would be 400 plus that 60 mile an hour wind, and you get 460 miles per hour. The speed against the wind would be 400 minus the wind speed, or 340 miles per hour. Distance with the wind would then, if it went for 4 hours, would be 460 miles per hour times 4 hours, or you'd get 1,840 miles. If I went against the wind, I'd have to go this 5 hours to get this match, but they don't match in this case. So what we're really doing is kind of guessing and checking and trying to get an idea, will this work, and we can do this stuff. Okay, so we've already described in the diagram how do you express going with the wind. Well, it would be the rate plus this wind speed of 60, and if you went against the wind, it would be the rate of the plane travel, right, minus the 60. So they get this, and D, they say let that represent distance traveled in miles. So they use this distance equals rate times time, or speed, they say, for rate. Well, we draw this table with wind, distance here, and then the rate, it would be the R plus 60, and the time would be 4. And these times they got from the original problem. They're saying if you went 4 hours with the wind and 5 hours against the wind, when would they cover the same amount of distance? So here are our equations they derive from this table, which is very handy work. And now we can get this. Probably, when I see things solved for a certain variable, it's almost always the best strategy to use is substitution. So they substitute in the R quantity, R minus 60, all times 5, in for the D in the first equation. Then we have an equation with one variable. We solve that and we get R equals 540. Now R means rate, right? So we're talking about going 540 mile an hour. That's the plane speed. So we check. We say, well, when the rate, or the speed of the plane, is 540 miles per hour, if it's going with the wind, it would be 540 plus 60, or 600 miles per hour. Okay? And if it went against the wind, it would be this 540 minus 60, which is 480 miles per hour. And then we check this. It's saying, well, if it goes 600 miles an hour for 4 hours, it would go 2,400 miles. And if it went 480 miles for 5 hours, you'd go 2,400 miles an hour. So the speed of the jet with no wind is 540 miles per hour. This is a very good tool or tips, right? You know, word problems always first thing. If you can draw a picture of any kind of math problem, that's usually the first thing you should do. So it says draw a diagram using an arrow or arrows to represent distance and direction, you know, basically of each object in motion. 2, organize the information in a chart. We can take those formulas, especially distance equals rate times time. That'll give you the columns of that chart. You need something to represent distance, something to represent rate, and something to represent time. And then going back to the word problem, you can usually pull out the specific information you need, or that it gives you, and then fills it in. And what it doesn't fill in are variables. Look for times, distances, or rates that are the same. You know, if things meet each other, you know, if they're going in the same direction, like that first example, they're going to go the same distance. Sometimes they might talk about how long will it take to get to something. Well, if it's a certain amount of time for each of these things that are moving to occur, well, that's what they're talking about. When this time is the same, that's when they meet or they've gone a certain distance. Translating to a system of equation allows for the use of 2 variables, and label the variables carefully. We want to make sure that at the end of this we know what they represent so we can answer our question. Always make sure that you have answered the question they've asked. Like I said, that happens a lot of times. You could spend 15 minutes working on a problem and then not answer the question. Well, that's it for 8.3, and more to come.